Hi, everybody. I just want to go through a little encoding and decoding lesson. So let's start with decoding. Ooh, let me rewrite that. Decoding. So we'll start with decoding, and I want to look at sort of an easy decoding, binary to octal, simply because I only need three binary digits to make an octal number, and that will keep our table a little bit smaller. So first, I'm going to draw the inputs, and I'll separate inputs and outputs by this double line. So the inputs, I'm going to write them as 2 to the 2, 2 to the 1, and 2 to the 0. And I'm doing that just so that I keep in mind that these inputs are actually representing a binary number, where 2 to the 0 is the least significant bit, and 2 to the 2 is the most significant bit. And then our outputs there on the other side of this double line will be the octal number. And with these outputs, if we were setting this up in the lab, octal number, we would have each output here going to a different LED. Right? So the idea is that we would use switches to input a binary number, and one of 7 LEDs would light up representing that binary number. So let's put in our possible input combinations. I'm just writing them all down here. And I'm showing the 0-0 combination, even though I'm not going to wire any light to that. That would be the no light on configuration. So for this configuration here, I'm just going to say no LEDs on, so they should all be off. And this second one would be a 1, a 2, a 3, a 4, a 5, a 6, and a 7. So for each of these outputs, we're saying a different LED is going to light up, representing the octal number that is formed by decoding these binary inputs, right? And if we think of our usual sum of products way of generating an equation for these, let's look at the example here with the octal number 5. I have 2 to the 2 being 1. I have 2 to the 1 being 0, so I'm going to invert it. And I have 2 to the 0. So, and that would be the combination that's going to make LED 5 go on. And that's our it's a product, right? We're ANDing. We need all of those inputs to actually be set to that at the same time. And that could be represented by an AND gate, 2 to the 1 bar and 2 to the 0. If we wanted our outputs to be active high output, so being the output is high when that particular input is chosen. If we wanted to have active low inputs, we could get that by adding an inverter at the end and using an AND gate. So we would add inverter for active low outputs. Okay, but in that way, we could have an AND gate for each of these possible combinations and wired to these same 3 input switches. So what we're saying here is that we're using switches, so 3 switches. And depending on the switches that we set high, we'll get a different LED coming on. So that is the process of decoding, and it is going binary to octal. Now I'm going to scroll up here a little bit and talk about encoding. So encoding is just going the other way, right? And we think of decoding as going from a more machine-based language, something that humans don't intuitively understand, like binary, to something that we can actually read very easily, like octal or decimal. And we're just looking at the first base digits of octal, so those are easily readable. So let's look at the other direction, encoding. So for encoding, we want to go from the octal number. So I'm going to have, I'm going to say here I have 7 switches, right? And depending on which switch is high, I'm going to get a particular set of lights on representing the binary number for that. So I'm going to have a 2 to the 0 output, a 2 to the 1 output, and a 2 to the 2 output. And again, this is least significant bit and most significant bit. And so my input switches, I'm going to have 1, 2, 3, 4, 5, 6, and 7. I could have the case where none of the switches are high, which would be the case where none of the output LEDs are on. So these outputs are going to go to 3 LEDs so that we can see that they're on. And of course, for a 1, we're expecting binary 1, then binary 2 for 2, and so on through the table like so. And in order to figure out what kind of gate we need to make these outputs, it's a little bit different in the previous case, because in the previous case we were looking at many inputs making one output, so we had to AND all the inputs together. In this case, we're looking at many different inputs where any one of them acting alone can trigger an output. So that is actually an OR condition, because take, for example, this most significant bit. If switch 4 or switch 5 or switch 6 or switch 7 is on, then we want this, this output to light up. And none of those switches are going to be on at the same time. So, and they don't need to be, it's just any one of them will trigger this output. So that case is an OR gate, and we would have 4, 5, 6, switch 4, 5, 6, or 7 going to our LED for 2 to the 2, which is the most significant bit, right? And so for the second LED here, it's switches 2, 3, 6, and 7. So any one of those will cause this to light up. So I can say switch 2, 3, 6, and 7, and this is going to be the 2 to the 1 output. And then the last case, it's 1, 3, 5, and 7. That's going to be an OR gate. That's my 2 to the 0 LED, and I'm going to connect it to switches 1, 3, 5, and 7. Any one of them high would set that LED. So if we put a number through this as a quick example, let's consider if we put input switch 6 high. So if I put 6 high, then that means this input goes high with the rest of them though, and this input goes high, which means we're going to get a 1 here and a 1 there, and this output will remain 0. That is the binary number 6, where this is our most significant bit. Okay, so so that's the process of encoding. And one of the things that we noted was in the lab, we built an encoder, but we didn't build our encoder with OR gates. We actually built it with NAND gates, and they were actually active low. So let's draw, taking the most significant bit example from above. Theoretically here, so here in our theory, we just talked about having switches 4, 5, 6, and 7, where they were active high, meaning a 1 is the switch being flipped, which should trigger the output, and this was going to the 2 to the 2 LED, which was also active high. When we get a 1 here, we want the LED to go on, and that's considered our active output. Now in the lab, that's not what we built. In the lab, we actually used NAND gates. So we connected this. We still connected it to switches 4, 5, 6, and 7. And we still connected it to the same LED. This was still an active high output, but these inputs were actually active low, which means I would leave all of these switches high normally and just put low the switch that I want. So in the case where in theory we had switch 4 low, 5 low, 6 high, and 7 low, in the lab we actually kept the switches high except for switch 6, which we put low. And then we got a 1 at the output, or a high at the output here to turn the LED on. So so that was the difference. And the question is, why are these two circuits equivalent? How can they both be encoding? They don't look the same, right? And to think about that, we have to go back to De Morgan's theorem. And De Morgan's theorem tells us that we can convert from an OR gate to an AND gate if we invert the inputs and the outputs. So De Morgan's theorem tells us that A or B is equal to A and B if we negate the inputs and negate the output. So if I'm going to draw that pictorially, it's like with our example there, it's like saying this is equal to this, because we can expand De Morgan's theorem for 4 inputs. So if we had 4 inputs, we can expand De Morgan's theorem. It's still true. So this is the case where, we've got our switch 4, switch 5, 6, and 7, and our output are 2 to the 2 LED. And this is switch 4, 5, 6, and 7, and our 2 to the 2 LED. Now, these two circuits are the same, but notice in the lab, we didn't do this. We didn't have inverters here, okay? And so recall that these inverters, these bubbles are representing inverters, and I could actually draw them separately as inverters. And you can imagine that I'm taking this bubble and sliding it back. Okay, so I'm going to draw that down below where I'm moving the bubbles back and changing them to the inverters that they represent. And then I've got my NAND gate. Okay, and I still have my 2 to the 2 active high LED here. Okay, and we still have our switch 4, 5, 6, and 7 here. And these inputs we said were active high right here. They're active high, meaning normally the switches are all low. So in our example, switch 4, 5, and 7 were low, but we flipped switch 6 high as being our input switch. Now, on the other side of the inverters, we've got high, high, low, high, right? And what we see there is We can get away without using these inverters in the lab to avoid having to use extra chips and wiring up extra chips if we go with active low inputs, where all the inputs are high except the one input that we want to be our triggered input in this case, and we set it low to be considered active. So what we built in the lab was this, what I'm circling in green, part of the circuit here, where we considered the inputs to be active low and then still had our active high output. And in that way, we could avoid having to wire up to additional inverters. And we also went with NAND gates because we didn't have four input OR gates, but we did have a chip with 4 input AND gates.